In this module, we explore the concept of thermodynamic potentials. These potentials allow us to comprehensively describe the equilibrium state of a system. Let's consider a simple closed system that has no internal variables. This means that there are no processes that need to be described by internal variables and no non-volume work is involved. For example, there is no matter exchange between the system and the surroundings and no chemical transformations of species inside the system. For such a system, we can express the fundamental equation of thermodynamics as the differential of internal energy dU is equal to the temperature T multiplied by the differential of entropy ds minus the pressure P multiplied by the differential of volume dV. This equation forms the basis for understanding how different variables describing the state of such a system interact with each other. In this way, it serves as a starting point for deriving thermodynamic potentials. In thermodynamics, even such a simple closed system can be described by a multitude of state functions or variables. This includes pressure P, volume V, temperature T, internal energy U, entropy S, enthalpy H, Gibbs energy G, Helmholtz energy A, and many others. Although all these functions characterize the state of the system, only two of them are independent. Once we have chosen two independent variables, all other state variables can be determined as functions of these two. The fundamental equation shows that the change in internal energy U is directly affected by changes in entropy S and volume V. This relationship suggests that the most straightforward and natural way to express internal energy is as a function of entropy and volume. Now, let's assume that we have an equation for the internal energy defined as a function of entropy S and volume V. The mathematical consequence of considering internal energy as a function of entropy S and volume V is that the differential of U can be expressed in terms of differentials of S and V. By comparing this expression to the fundamental equation of thermodynamics, we can see that two thermodynamic relations can be derived for the system under consideration. The temperature T is the partial derivative of U with respect to S at constant V. The pressure P is the negative partial derivative of U with respect to V at constant S. This means that if we know the internal energy as a function of entropy and volume, we can directly determine the temperature and pressure for any state of the system. This demonstrates the usefulness of expressing internal energy as a function of entropy and volume in thermodynamic analysis, as it allows the determination of other state variables. In fact, it allows calculation of all state variables typically used in thermodynamics. Furthermore, the first of these two equations is an alternative definition of temperature in thermodynamics. The internal energy U is an example of a thermodynamic potential. In general, a thermodynamic potential describes the equilibrium state of a system completely when expressed as a function of its natural variables. Another key property of a thermodynamic potential is that it has the dimension of energy. This allows a thermodynamic potential to quantify energy changes in a system. As we have just seen, knowing internal energy as a function of entropy and volume, we can determine the temperature and pressure and derive all other state variables of the system. Therefore, entropy and volume are the natural variables of the thermodynamic potential U, internal energy. Other thermodynamic potentials include quantities such as the enthalpy H, the Gibbs energy G, and the Helmholtz energy A. The natural variables differ for each thermodynamic potential. It is of course possible to express the internal energy U as a function of other state variables, because these variables are all interrelated. One common choice is to define the internal energy in terms of temperature and volume. In this representation, the total differential of U is given by the partial derivative of U by temperature T at constant volume multiplied by the differential of temperature dt plus the partial derivative of U by volume at constant temperature multiplied by the differential of volume dV. In this expression, the first partial derivative is defined as the heat capacity at constant volume Cv. The second partial derivative is referred to as the internal pressure at constant temperature pi T. These derivatives define important thermodynamic properties, but they give no information about other state variables, such as entropy or pressure. Therefore, expressing U as a function of T and V describes the system only partially. To account for all possible interactions in a thermodynamic system, we expand the fundamental equation of thermodynamics to include additional generalized forces and generalized coordinates. By considering additional interactions, we obtain a more comprehensive form of the fundamental equation. The differential of internal energy du is equal to the temperature T multiplied by the differential of entropy ds minus the pressure P multiplied by the differential of volume dV plus the sum over I of the generalized forces xi multiplied by the differentials of the corresponding generalized coordinates dxi. In this extended form, the internal energy is expressed as a function of its natural variables entropy S, volume V, and other generalized coordinates xi. Other state variables such as temperature, pressure, and generalized forces are defined through the partial derivatives of U with respect to these natural variables. Temperature T is given by the partial derivative of U with respect to S at constant V and all xi. Pressure P is given by the negative partial derivative of U with respect to V at constant S and all xi. Each generalized force xi is determined as the partial derivative of U with respect to the corresponding generalized coordinate xi at constant S, V, and all other generalized coordinates xg. This formulation enables us to define and evaluate additional thermodynamic properties for complex systems through these derivatives. The enthalpy H is another thermodynamic potential. Its total differential can be derived from that of the internal energy and is given by the temperature T multiplied by the differential of entropy ds plus the volume V multiplied by the differential of pressure dP plus the sum over I of the generalized forces xi multiplied by the differentials of the corresponding generalized coordinates dxi. Here we have substituted the expression for du from the fundamental equation of thermodynamics. This equation shows how enthalpy H is expressed as a function of its natural variables entropy S, pressure P, and other generalized coordinates xi. When H is defined in terms of these variables, we can obtain the following thermodynamic properties as partial derivatives. Temperature T is given by the partial derivative of H with respect to S at constant P and all xi. Volume V is given by the partial derivative of H with respect to P at constant S and all xi. Each generalized force xi is given by the partial derivative of H with respect to the corresponding generalized coordinate xi at constant S, P, and all other generalized coordinates xj. In many practical applications, entropy S is not a convenient variable to work with. It is challenging to measure or control entropy directly. Therefore, the practical application of equations derived from the properties of the internal energy and enthalpy as thermodynamic potentials is limited. Instead, the Gibbs energy G is another thermodynamic potential that is much more useful for processes occurring at constant temperature and pressure. The latter are common conditions in both laboratory and industrial settings. The total differential of the Gibbs energy G is given by negative entropy S multiplied by the differential of temperature dT plus volume V multiplied by the differential of pressure dP plus the sum over I of the generalized forces xi multiplied by the differentials of the corresponding generalized coordinates dxi. This expression shows how Gibbs energy is expressed as a function of its natural variables temperature T, pressure P, and other generalized coordinates xi. When defined in terms of these variables, the Gibbs energy provides a convenient framework for deriving the following thermodynamic properties. Entropy S is the negative partial derivative of G with respect to T at constant P and all xi. Volume V is the partial derivative of G with respect to P at constant T and all xi. Each generalized force xi is the partial derivative of G with respect to the corresponding generalized coordinate xi at constant T, P, and all other generalized coordinates xj. These properties make G particularly effective for characterizing systems where temperature and pressure are the main variables controlled. The Helmholtz energy A is another thermodynamic potential. Its total differential is given by negative entropy S multiplied by the differential of temperature dT minus pressure P multiplied by the differential of volume dV plus the sum over I of the generalized forces xi multiplied by the differentials of the corresponding generalized coordinates dxi. This equation shows how A is expressed as a function of its natural variables temperature T, volume V, and other generalized coordinates xi. From this differential form, we can derive other thermodynamic properties. Entropy S is the negative partial derivative of A with respect to T at constant V and all xi. Pressure P is the negative partial derivative of A with respect to V at constant T and all xi. Each generalized force xi is the partial derivative of A with respect to the corresponding generalized coordinate xi at constant t, v, and all other generalized coordinates xj. This demonstrates how the Helmholtz energy A can be particularly useful to describe the system's behavior when temperature and volume are the primary variables controlled. The Maxwell relations are a set of equations derived from the equality of mixed second partial derivatives of different thermodynamic potentials. Each thermodynamic potential produces a corresponding Maxwell relation which links different state variables. The Maxwell relation derived from internal energy is the partial derivative of temperature T with respect to volume V at constant entropy S and all generalized coordinates xi is equal to the negative of the partial derivative of pressure P with respect to S at constant V and xi. From enthalpy, the partial derivative of T with respect to P at constant S and xi is equal to the partial derivative of V with respect to S at constant P and xi. From Gibbs energy, the partial derivative of S with respect to P at constant T and xi is equal to the negative of the partial derivative of V with respect to T at constant P and xi. From Helmholtz energy, the partial derivative of S with respect to V at constant T and xi is equal to the partial derivative of P with respect to T at constant V and xi. These relations, although they may seem worthless at a first glance, are powerful tools for connecting seemingly unrelated thermodynamic properties in unexpected ways. They allow us to express one property in terms of another, making it easier to predict how a system will behave under varying conditions. In particular, entropy, a property that cannot be measured directly, is brought into connection with other directly measurable state variables. Moreover, more complex relationships connecting these variables with generalized forces and coordinates and between different generalized forces and coordinates can be built using the same approach. This expanded use of Maxwell relations helps us to uncover deeper connections between the properties of a system, providing a comprehensive framework for analyzing thermodynamic behavior in various contexts.